repulsive all across the world. These people are watching our elections. They understand that we have a legal process. They understand.
How's everyone doing today?
Pretty good.
Good. Okay.
Pretty good. How are you?
Good. I forgot to send out the exam, so I have it, but I'll send it at the end of class. All right, so we are gonna continue working here. I'm almost ready to start 8.2, which is our section on series, but I wanted to get two things out of the way first. So these are things that I failed to mention during last lecture. The first one is a theorem, and it just helped. This is all in reference to sequences. The first part here, the theorem says that if you have a sequence and you take the absolute value of that sequence and you find that the sequence converges to 0, then you can conclude that the sequence without the absolute value must also converge to 0. So let me give you an example. Let's say that we have the sequence a sub n equals -1 to the n over n squared plus 1. All right, so if I wanted to know if this converged, there's two ways I could do it. I could just say that, you know, as I let n go to infinity, if I take the limit of this as n goes to infinity, I could say that the top is bounded because it's always going to be between -1 and 1, or it's either going to be -1 or 1. And I can say that the bottom is headed to infinity, and we know that that goes to 0. That's one way I could conclude that that sequence converges to 0. But if I use the theorem would say that if we take the absolute value of this sequence, then when we take the absolute value of the numerator, it doesn't matter if 1 or -1 comes out. If we take the absolute value of that, we should just get a positive 1. And then over n squared plus 1, the absolute value of n squared plus 1 is still n squared plus 1, because both n squared and 1 are both positive. And this goes to 0 because we have a fixed number over infinity, which we know goes to 0. So this theorem will come up later. If we're ever looking at a sequence and we're trying to figure out whether or not it converges, if we can show that the absolute value of the sequence goes to 0, then we can conclude that the sequence itself must go to 0. Now you have to be extremely careful with this. I'm going to give you another example over here. Look at the sequence a sub n equals -1 to the n. That's it. That's the sequence.
That's alternating.
Yeah, it is. And it would just give us -1, 1, -1, 1. That's what it would do. Now, if we take the absolute value of that sequence, won't that always just be 1?
Yeah, positive.
Because we're always going to be taking the absolute value of the number. And if it's -1, it'll be 1. If it's 1, it'll stay 1. So we could say that the absolute value of this thing heads to 1, right? Because it's always 1. But does that mean that the original sequence, does that mean that that original sequence goes to 1 also?
No.
No, it doesn't. And the reason it doesn't is because the theorem says that if the absolute value of the sequence goes to 0, then the original sequence must also go to 0. But here, the absolute value of this sequence went to 1, and so the theorem does not apply. So you just have to be careful. I'm not telling you that in order to find out if a sequence converges, you can just look at its absolute value. The only way to apply the theorem is if the absolute value went to 0, okay? So just be a little careful there. Now, the second part of sequences that I didn't really address was, what if you have a sequence that is a sequence where you have a number to a power? So a specific example of this would be, let's say we have the sequence 1/2 to the n. So that sequence is just 1/2, 1/4, 1/8, 1/16. Okay, if we had that sequence, does this converge or diverge? Well, this says that if we have a sequence like this, where r here is this number, then the sequence will go to 0, converges to 0 if the absolute value, if r is between 0 and 1. So if this number here is, 1/2, 1/4, 0.2, any number between 0 and 1, we will have convergence to 0. If the r is bigger than 1, then it'll diverge. So if you had something like this, let's say it was 2 to the n, then of course that would just be 2, 4, 8, 16. And you can see these things are just blowing up. They're just getting bigger and bigger and bigger. So this would diverge. Of course, this would converge. So just remember that. If you have a number that's raised to a power, it'll converge to 0 as long as that number here, the base you could call it, is between 0 and 1, and it will diverge, get bigger and bigger if the base is bigger than 1. Okay, that makes sense?
Yes.
Okay, all right, we're ready to start 8-2. Series. Okay. So when it comes to series, I have to define what a series is first, right? We know what a sequence is, right? A sequence is a list of numbers. Let's just remind ourselves of that. A sequence is just a list of numbers. Now, we know that we can also look at a sequence as being a function that goes from the natural numbers into the real numbers, all that. But for now, it's just a list of numbers. A series is simply the sum of the numbers in a sequence. That's all it is. We're just going to take all those numbers in the list and add them up. Add them. That's it. That's all a series is. Now, you're either going to have a finite. So a series can be finite or infinite. And that's because sequences can be finite or they can be infinite. So for example, if I were to give us this sequence, 1, 2, 3, 4, that is a finite sequence, right? It's a finite sequence. Then the series that corresponds to that sequence would be 1 plus 2 plus 3 plus 4, and that would be a finite series because it's a finite number of additions. So what would that be? I think it's 10, right? Okay. So notice that our answer is just a number, isn't it? The series for this sequence is this number 10. That's not very interesting to us. We're not really concerned too much with the series for a finite sequence because we know that we can, if someone gives us a sequence of numbers and there's a finite number of them, 100 of them, 1,000 of them, 1,000,000 of them, we could add those up, right? And we would eventually get an answer. What's more interesting to us is something like this. What if we have an infinite sequence, like 1, a half, a third, a fourth, forever, right? What if that goes on forever? Infinite sequence. Then the series for this would be 1 plus a half plus a third plus a fourth plus dot, dot, dot forever. And the question is, what happens to that sum? Does it just keep getting bigger and bigger and bigger? What happens, right? So in general, here's what we have. Let's say we're given an infinite sequence. A1, A2, A3. So say we're given an infinite sequence. The series, right? The series for this would be A1 plus A2 plus A3 plus forever, right? This would keep going forever and ever. And so one of the first things we need to kind of establish is a notation for this. And so what we're going to go back to is sigma notation. We talked about this when we were doing Riemann sums. A shorter way of writing this would be to use the capital Greek letter S, and then we put down here k equals 1 to infinity, and then here we put A subscript k. And let's just see if this makes sense. Remember, the bottom of this is the starting point. We call this the starting number of our index. And then this is where we end. And then this is the expression we're evaluating. So we always start with k here being 1. So we replace that k with 1, we get A sub 1. Then we say plus, and then we let k be 2. That becomes A sub 2, and that's this one. And then we let k be 3, A sub 3. And then we keep doing that forever, and we never stop, right? So this would be a nice notation for the sum of an infinite sequence, right? Or I should say, that is the notation we would use for an infinite series. Any questions? No? Okay. So next concept, and this is very important, this next concept. Partial sums. Okay, and when we talk about partial sums, we're still looking at infinite series, all right? We're still talking about an infinite series, but we're going to be talking right now about what's called a partial sum of an infinite series. So let's say we have a sequence, A sub 1, A sub 2, A sub 3. Then we will define the, what we call kth, that's kth, partial sum. Hold on, sorry, take that back. Let's do nth partial sum. Nth partial sum as follows. We write S, capital S, subscript n equals the sum k equals 1 to n of A sub k. So can somebody tell me, like in layman's terms, or like just talking to someone on the street, although you probably never be talking to someone on the street about partial sums, what the hell is this? What is this doing? What is this sum actually doing?
Is it like the sigma for the series, like the sum of the whole series or something?
Is
Is it doing like a loop of series?
The sum, it's the sum of like a part of it, not the whole thing.
That's right. It's just a sum of part of the infinite series, right? In this particular case, this would be just the sum of the first n numbers in the sequence. So that's where the word partial comes from. We're not looking at the infinite series. The infinite series is the sum of everything, right? That's what this is here. It's everything added up. A partial sum is just the sum of the first n numbers. So we are defining this, okay? We are defining what I have here in green. This is a definition. We are calling this the nth partial sum. So let me give you an example. If I write S sub 1, what I mean is I want you to just take the sum, k equals 1, and where do I want you to stop?
1.
1, and I want you to add up the a sub k's. So that means you're going to start with k being 1, replace that k with 1, that's just a sub 1. And then you say plus, but wait a minute, we're supposed to stop at 1, right? So isn't S sub 1 just the first number in the sequence, right? It's just that number. But then what would capital S sub 2 be? Well, that would be the sum k equals 1. Where do I stop this time?
2.
2, that's of this. And now you're going to do a sub 1, but now plus a sub 2. So now you're adding up the first 2. You see how this is working? The third partial sum would be the sum k equals 1 to 3 of a sub k, which would be adding the first 3 together. Now, do you agree with me that if I have the sequence, right? If somebody gives me the sequence of numbers, if I have this, then I could actually come up with a numerical answer for this. This right here is going to be a number, isn't it? And if I have the first 2 pieces, I can add those together and I'm definitely going to get a number. And if I have the first 3, I can add those together and I can get a number. For each of these, I'm going to get a number, right? Right? And remember, the whole goal, okay, the whole goal is to see if there's any possibility of us adding up all infinitely many of them, right? Can we add them all up and get an answer? So guess what? If this first partial sum is a number, and the second partial sum is a number, and the third partial sum is a number, then isn't this just a list of numbers? Isn't this just a list of numbers?
Yes.
Yeah, right? Now, the first number in this list is just this guy right here. It's just the first one in that sequence. The second number in this list is the first 2 added. The third number in this list is the first 3 added. The fourth number is the first 4 added. What do you think I'm going to ask you about this sequence? Because this is now a sequence, isn't it? What do you think I'm going to ask you about this sequence?
If it diverge or converge?
Does it converge or diverge, right? Does it converge or diverge? So since this is a sequence now, this is just a sequence. It's a new sequence, right? I'm going to put it's a new sequence. So does it converge or diverge? So that means we need to ask ourselves this. What is the limit as n goes to infinity of S sub n? That is the $1 million question. What does this go to? If I let n go to infinity, then I'm basically saying add up the first n and let n go to infinity, right? And that would represent the infinite sum, which is what the series is. So this is really weird. We start with a sequence, then we start talking about these partial sums, those partial sums create a new sequence. And now we're asking if that new sequence converges or diverges. All right.
Now, is it the same as you mentioned at the beginning, that if it's less than one, is going to, if the sum so does it diverge if it's less than one, or if it approaches at one, is it going to diverge? Is that going to be the case for this too?
Yeah. So since this is a new sequence, right? This is just a new sequence. Since this is a new sequence, everything that we've already talked about in terms of sequences applies to this sequence.
Okay.
All the rules that we have for sequences are valid for this. The thing is, the numbers in this sequence they have a meaning to them. They are the sum of the numbers in another sequence. So let me try and illustrate this like visually, okay? I think it might be better if I try and illustrate this with a picture.
So is it like a sum of different series?
It's this. We have to be careful with our language. What did you say?
Like I know that series is a sum of sequences, but is this a sum of series, the new sequence?
No, the new sequence is just a list of numbers where each number represents a partial sum of another sequence. Let me show you the illustration, okay? I think it might help if I show you this. So this illustration that we see here, the original sequence we're starting with is 1 over n. So that sequence is the sequence 1, 1/2, 1/3, 1/4. Got it? Okay. Now, if I were to graph this sequence, that's this picture right here. That's the black dots. I don't know if you can tell those are black.
Yep.
So if I, no, I don't want that. Yeah, like that. No. That's what that 1 over n looks like. You start out, the first number is 1, the next one is 1/2, the next one is 1/3, 1/4, 1/5, 1/6, 1/7, right? Okay, what you see over here is this is the sequence generated by the partial sums. So this right here in blue, let me see if I can make my thing blue here. This right here, that didn't work. This right here is the sequence S sub n. Now let me try and tell you what that sequence is. The first number in this sequence is just the first number here, 1. But the second number, that second dot, is not 1/2, it's 1 plus 1/2. It's the first 2 over there added. And then the third number in this one is the first 3 of these added, 1 plus 1/2 plus 1/3. And then the fourth one here is going to be 1 plus 1/2 plus 1/3 plus 1/4. Do y'all see what I'm saying?
So it's like a sum actually.
It's exactly a sum. And so you're almost like stacking up. It's like you're taking how tall this one is. So like this one right here. Let me do this one. This one right here. The third number here, which would be 1, 2, would be that number right there. That one is adding up the first 3. That means I'm taking the heights of these first 3 points, taking how tall they are, and I'm stacking them on top of each other, and that's creating this new point over here. Does that make sense? The next one would be those 3 heights, but now you add this height. You're with me? Now, the question was, does this one converge? Okay, we know this converges, right? 1 over n. 1 over n converged. We know that the original sequence, we know that this converges to 0, and you can see it in the picture. It goes down, right? And we know if we let that n go to infinity, this thing would go to 0. We know that. The question is, does this one converge? If you start adding these up, right? If you start adding all these up, this is what it starts to create. So I'm going to start going. What's that?
I don't think so. It converges.
You don't think
it
so?
just-
Okay. I mean, that seems logical. Let's just take a look. Right now, I've added up just these, okay? And if I add those up, this last one right here is 4.17456. That's how tall this one is. Okay, so where am I at? I'm on the 36th. So this dot right here represents the first 36 of these added up. That's how tall that dot is. Understood?
Mhm.
Okay, so I'm going to start dragging this out. Let's take a look at what happens. Look at my blue one over there. Look what's happening. I just broke 5, didn't I?
Yeah.
Now I'm bigger than 5. Okay, that's the first 100. Make my points a little smaller. Okay, let's go out. Let's look at the first 400. And let's just keep an eye on that number, 5.6. Now it's at 6. Keep going. Okay, that's the first 400 of them. So if you add up the first 400 of these, you get 6.56993. I'm going to go out to the first 800 of them. Okay, so now I'm adding up the first 800. Oh, now we've broken 7, haven't we?
Mhm.
The question
it's-
is, go ahead.
Can we say that these shows that the result it's basically going to infinity?
Well, it looks like it is, right?
Yep.
The question becomes, how do we show that, right? We can't just look at the graph and be like, oh yeah, okay. It looks, I'm just trying to get you to see visually what we're doing. The difference between A sub n, which is the sequence we're starting with, and S sub n, which is a new sequence, which represents the sum of the partial sums of the original sequence. That's the main idea here. We still don't know how we are going to answer this question. It looks like it's going to infinity. It does, okay? But maybe there's a horizontal asymptote up here. Maybe there is. Maybe it's bounded above. It's hard to say right now.
What if, like, since you said when you were showing us the example, it was 1/2 plus 1 plus 1/2, then, like, you know how we were just summing everything up?
Yeah.
So with that being said, since everything is just getting added onto it, isn't it obvious that it's going to be infinite because everything is getting added?
You would think so, right?
Yeah, I
You
would think so.
so.
That
Yeah. And it turns out that sometimes it does go to infinity and sometimes it does not. Sometimes it converges. So let me show you a different example, okay? I think what's being proposed is that, look, if all you're doing is adding more stuff each time, then it's got to blow up eventually. It's got to blow up, right? Like it's just going to keep getting bigger. Not the case. And we saw this with integrals. Remember our integrals that went to infinity? We were trying to find the area underneath. And we said, wait a minute, sometimes that area was finite, sometimes it was infinite. It depended on the function, okay? Those were improper integrals. This is a similar idea. We're adding numbers up, but just because you're adding a bunch of things together forever, it does not mean that it overfills the cup and becomes infinite. This one actually does, but I haven't shown you why. Let me show you a different example. Okay, let me show you a different example. Let me pull this back. Let's get this into more reasonable numbers here. And let's look at 1/n squared instead of 1/n. Okay, so we are looking at the sequence A sub n equals 1/n squared. We know that one converges. Okay, we can see it here. We also know if we take the limit as n goes to infinity of this, it's obviously going to go to 0. So we know that this we know that this thing goes to 0. We can see that in this picture. All right here, they drop down fast, they head to 0. Take a look at the series, take a look at the partial sums, this new sequence. Where is that headed? So does that look like it's growing and it's going to keep growing and growing and growing? I don't know. Let's go out to the first 800. Look at that.
I guess the exponent matters.
I think that square did something, didn't it? Because look, it looks like we're at 1.64. I mean, If I go out to the first 1200, now my computer's starting to slow down, okay, because it's running this algorithm. But look, it looks like we're not getting past like 1.6, right?
Mm-hmm.
Now we've only gone out 1200 places and we can go out to infinity. So maybe it does blow up. Maybe eventually it just slowly grows, but it looks like it's possible that this one converges. Do y'all see that? Maybe it does. So our task at this point, let me pull all this back so my computer doesn't sit here freaking out. Our task at this point, okay, is to understand that we create a new sequence and we want to know whether or not that sequence converges or diverges. All right. One more definition, then we'll do some examples. Okay, if S sub n converges to some number S, okay? If that new series, that new sequence we just found, if it converges to some value S, then we say S is the sum of the infinite series. In other words, this S is equal to the sum as n equals 1 to infinity of a sub n. Okay, I'm going to back up just so we're clear on this. We started this whole idea saying, look, a sequence is a list of numbers. A series is the sum of those numbers. The series can be finite or infinite. Finite ones aren't very interesting to us because we can always add up, you know, so many numbers and stop and add that up and get a number. We're more concerned about the sum of an infinite sequence. So what we did is we started with the general sequence. We said that if you could add them up forever, here's the notation we would use. This notation represents the sum of these forever. Then we said, all right, let's define this new sequence of partial sums. And now we ask, does this converge? We're saying that if it does converge, that whatever it converges to is actually the sum of that series. It's the infinite sum. Now I'm using n here. You could, if you want here, that's called a dummy variable. You could replace that with k. And then it would look exactly like this formula right here. It's the same thing. Okay, that's what we refer to as a dummy index. We usually use n or k. Right, so we have a lot of work to do, okay? This is just to make sure you understand the general idea of what we're trying to do, right? We have done nothing in terms of figuring out whether or not we're gonna be able to figure out what this picture over here is doing, all right? All right, so let's do our first no, I'll give you the theorem before we do the first example. Okay, let's do a theorem. We do have a theorem that will help us. Okay, this theorem does help a little bit. This theorem says if your sequence, so we have to be very careful that we're with our language here. A sub n is a sequence, all right? That's the original sequence we're talking about. If A sub n converges to L, remember that arrow means it's going to L. And L is not equal to 0, then the sequence S sub n diverges. In other words, this sum diverges. I shall give you an example. Okay, let's do an example. Example. Find the sum k equals 1 to infinity of k plus 1 over k plus 2. Now, just so you know, I could have written this problem this way, using n instead of k, and it would be the same exact question. All right, these are both totally equivalent to one another because the k is a dummy variable and this n is a dummy variable. All right, so what you have to see here is first, what is a sub n? Because this theorem says what's a, if a sub n is going to L and L is not 0, then the sum diverges. So can somebody tell me from here, or let's work with the blue one. Can somebody tell me from here what a sub n is? What's the thing that
1.
we're adding up?
1.
N plus
No.
1 over N plus 2?
1 over 2.
It's n plus 1 over n plus 2. Okay, all a sub n is this piece right here. Okay, that's a sub n.
So basically the whole thing is a sub n.
Yes, and then remember, this just means we're adding them all up, right? So this is like the original sequence, right? That's the original sequence. That's a sub n. That's the original sequence. And the sum means we're going to add them all up. So take a look at this. If we look at this a sub n, what does that a sub n converge to? Well, that means you have to take the limit, right? You have to take the limit as n goes to infinity of this. And can you all tell me quickly what that is?
1 over 2?
Infinity over infinity.
This is infinity over infinity. So you would have to switch it to a function of x.
Just 1.
Then you'd have to use L'Hopital's rule.
Can I do 1 over n
you-
instead?
You what?
Can I multiply with 1 over n?
You could do 1 over n. Yep.
Yeah, okay.
But either way, however you do it, everyone should be comfortable right now in this class to be able to get that goes to 1. Okay, you could just do L'Hopital on it, derivative top and bottom, you get 1 over 1, the answer is 1. Do you all agree with that? So what does this theorem tell us? If we have a sequence that converges to some number L, and that number L is not 0, then what can we say about the sum of that sequence?
That's diverges.
It's divergent.
So
And the
isn't it-
reason it's divergent is because let's just look at this sequence. Let's just look at the numbers here. If I plug in 1, I get 2/3, and then I get 3/4, then I get 4/5, and I get 5/6, I get 6/7, 7/8, 8/9, right? So if I start adding these up, do you agree that whatever this one is, this next one is bigger than it, right?
Yes.
And then the next one's bigger than that. Next one's bigger than that and bigger than that. So what you're doing is you're stacking these on top of each other, and each one that you stack on top is bigger than the one before. That thing should blow up and it should become infinite. Does that make sense?
Yes, but
Because
isn't
each
it the
Successive one's
same?
bigger.
Isn't it same as the one you first told us about, the an going towards 0? The one with the, like, if the absolute value of n is 0, then it converges. But if it's more than 0, then it diverges.
Okay, I'm going to say the answer to your question is yes and no. Okay. If the sequence, okay, if the sequence goes to something other than 0, right? Other than 0. So if the thing we're trying to add up goes to something other than 0, not 1, but other than 0, anything other than 0, we can say that the series, not sequence, the series diverges. Let's say that again. if you're looking at the sum of a sequence and the sequence converges to something other than 0, then the series diverges. Understand?
Okay, I understand. The
Now-
first one was related to the sequence.
That's
This is
right.
series.
That's right. Okay, so now I'm going to go to my formula sheets, and we have this thing series test, right? See the series test? The very first test on here is what we call the nth term test. And that's exactly the theorem I just put down for you. It says, look, well, first it's called the nth term test. It says, let's say you have a series, okay? You're adding up a bunch of things, and this right here is a sequence. That's our sequence, right? So we're adding up the pieces of a sequence. If the limit as n goes to infinity of that sequence, of the sequence, is not 0, right? Something other than 0, then what's the conclusion? It diverges, okay? So if this goes somewhere other than 0, it diverges. Now, what if it goes to 0? So what if that thing actually went to 0? What if this limit gives us 0? What do you think happens?
It converges to 0.
Okay, that's what you would think, right? We have to be very careful. This is where logic comes into play. All this test is doing, sometimes this is referred to as a test for divergence. This test says that if the limit of the sequence goes to something other than 0, you're guaranteed to have divergence. But if the limit of this does go to 0, if it does, the test is inconclusive, which means it might converge, but it could also still diverge. The test only guarantees you divergence. It does not tell you anything about convergence. So let me illustrate this with an example, because I know this is confusing, right? That's obviously, I've done this too many times. I know that this is a confusing concept. So let me show you this in 2 new problems, all right? And I'm going to do them side by side. So let's say we are comparing this 1 over n squared, n equals 1 to infinity. Let's compare that to this one. Now, do you remember I showed you these 2 a minute ago?
Yes.
Yeah, I showed you, this was 1 over n squared. And we said it looked like this right here was converging, right? But when we did 1 over n, it looked like this kept on getting bigger and bigger and bigger. That's exactly what we're looking at right here. So let's try this nth term test. Let's see what happens. So I'm actually going to say that. I'm going to try the nth term test right now. So that means I need to take this sequence, a sub n, which for us here is 1 over n squared. I need to take the limit as n goes to infinity of that, 1 over n squared. And we all know that that's just 0, right? So what is our conclusion? This is very important. What is our conclusion?
Inconclusive.
Inconclusive. We don't know shit. Okay, basically we don't know anything. All right. We don't know if this series converges or diverges. We have no idea. The only thing this test is good for is if this number right here comes out to be something other than 0. If it comes out to be anything other than 0, you can say it diverges and you're done. All right. So right here, I would just say test fails. And so what does that mean we're going to need to do? Probably another test. And guess what, everyone? We have plenty of tests, right? We have plenty of tests. We just need to go through and learn them all, okay? So we don't know yet, all right? Still inconclusive, we don't know. So look at this other one. Let's do the nth term here. If we do that, the sequence we're dealing with now is 1 over n. And if we take the limit as n goes to infinity of 1 over n, we get 0 again. And in the nth term test, getting 0 makes us very unhappy because that means the test fails.
But doesn't it converge?
Nope, don't say that. Because this nth term test is a test for divergence only. It's kind of like this. It's kind of like this. And this is such a terrible analogy. It really isn't like this. I don't know. No, it's not a good enough analogy. I'm trying to think of an analogy. It's like, no, that doesn't work either. Okay, yeah, let's do it this way. Yeah. This is a pregnancy test, okay? Normally a pregnancy test, they'll have something like this where like a line will be there, and if you're pregnant, a second line will show up or something like that, all right? This test we have is a test that will just, if a certain, so this test says if 2 lines come up, right? No, see, you can't use this test because when you're pregnant, you're either pregnant or not pregnant, right? It's one or the other. See, this test doesn't even work like that because all it does is test to see if you have divergence. That's all it does. It just tells you if you have divergence. So if okay, yeah, I can do it this way. Here, we can still stick with the pregnancy test. So let's say that this pregnancy test, 2 lines show up, okay? 2 lines means you're pregnant. Okay, let's say that the instructions said, sorry, I can't even write. Let's say 2 lines means you're pregnant. You read the instructions and that's what it says. If you see 2 lines, you're pregnant, all right? But it says not 2 lines. You could be pregnant or not.
Wait, what?
Okay, so think about the different possibilities. If we take the test and in the window we see 2 lines, what can we conclude?
You're pregnant.
We're pregnant.
Pregnant.
But if we don't see 2 lines, like let's say we see 1 line, or maybe we don't see any lines, then what can we conclude?
You could be pregnant.
You could be pregnant. So these two, this means that the test was inconclusive. That's what this means. It's almost like a defective pregnancy test. The only way you know for sure you're pregnant is if you see 2 lines. If you don't see 2 lines, well, you might still be pregnant. Okay? You might. So you better go get a different test. And that's what we're going to do. We're going to use a different test. Now, pregnancy tests don't work that way, but trying to give you an analogy, this test is like only testing for the 2 lines. The 2 lines means the limit is something other than 0. So if this limit is something other than 0, that's like getting the 2 lines and you're definitely divergent. But if you get 0, it's like you didn't get the 2 lines, so you don't know, you might still be pregnant, you might not. So you might still converge or you might diverge. Does that make any sense at all?
Mm-hmm.
Okay. All right. So we still don't know. These are still open questions. We have no idea. We have no idea whether or not they converge or diverge. As you might expect, the biggest mistake I see is that students will take this, they'll get that the limit is 0, and they will say the series converges, which is absolutely wrong. Now, does the sequence converge?
Yes, the
Yeah,
sequence
the sequence
converges.
converges. That's not what we're asking. We're saying, does the series converge? And you don't know anything yet, okay? So we have a lot of open questions, but it is a useful theorem because one of the first things you ever want to do when you have a problem is just check that, see what happens. Here's another example. This one freaks people out. Sum n equals 1 to infinity of arctangent of n plus 1 over n plus 2. Okay, so think about this one right here. The sequence we need to look at is this. So if we take that and we take its limit, as n goes to infinity, of arctangent of n plus 1 over n plus 2. When we take that limit, we already know that the inside of that goes to 1, right? And then arctangent of 1, what's arctangent of 1? So at
Zero.
what angle on what angle on the unit circle is tangent 1?
Pi over 4.
Pi over 4. So this is pi over 4. What can you tell me then? If this limit is pi over 4, what can you tell me about the series?
Divergent.
Pi over 4.
Divergent.
It's divergent. It's divergent because the answer was pi over 4, and pi over 4 is not 0. As long as this limit is not 0, the series diverges. See, the sequence converged to something other than 0, so that tells us that the series diverges.
I have a question. How is it 1? Like, are you taking the...
Well, we just did this problem. N plus 1 over n plus 2 was the previous problem. Or no, it was right. Oh, this one right here. Remember that went to 1? So I just, L'Hopital, you could use L'Hopital. Okay,
So on this, the square, the arctangent, that is the series, right? Not the sequence.
no, arctangent, all this, that's the sequence that we're adding up. The
Okay.
series is the whole thing added to get all those added together. Right? All of those together is the series. This right here, just that piece, is the sequence that we're adding up.
Okay.
All right.
What happens if the sequence doesn't converge?
If it just diverges itself? Great question. Great question. What do y'all think?
I think
What do
it's
y'all think?
inclusive.
Inconclusive, because what does the theorem say? Well, no, I mean, that's a good question. That's a great question, because the theorem says that if you don't go to 0, right, you diverge. Right? If you don't go to 0, you diverge. So what if you go to the limit does not exist? Right, like this.
It is not 0. That is not 0.
That is not
But-
0, right?
Can't you take the L'Hopital rule to make sure that
Well, it would depend on this. It would depend on the sequence. Look at this one right here. Here's our sequence, right? If we take the limit as n goes to infinity of sine of n, this does not, that does not go to 0, does it?
No.
As n goes to infinity, that thing is like scattered all over the place, right? It's like up and down all over, but it's definitely not going to 0, right? And so your conclusion would be that this series does what?
diverges?
Diverges. As long as it's not 0, anything other than 0, you're guaranteed divergence. Good question, Cameron. Did I address that question? Was that kind of what you were saying? Okay. All right, another one, I don't want to get too caught up on this, but how about this one? Well, let's take the limit as n goes to infinity of -1 to the n. Well, that limit doesn't exist because it's just switching back and forth, 1, -1, 1, -1, right? So that would not go to 0, which means this would diverge.
Can't you take the absolute value of it?
Well, if you do that, remember, what did we say? If we take the absolute value of this,
Has to go to 0, right?
it has to go to 0, right? That would be 1, but that's not 0. So that means that this thing doesn't go to 0.
Which is another divergent.
No, be careful. No, we can't, I'm saying we can't use this because this doesn't go to 0.
Okay,
So you can't be looking at the convergence or divergence of this sequence by using that theorem because this doesn't go to 0. So you can't draw any conclusions from this about that. And which means you can't draw any conclusions about that. The difficulty students have here is trying to keep separated the sequence from the series. There are two different things here. So you have to know what you're looking at, right?
So how do we know which theorem goes with series and which one goes with like?
How do you know with what? With which what?
So what theorem goes with series and what theorem goes with the sequences?
Well, that's your job, right? You got to figure out what goes with what. You have to figure out, I've presented everything in the section on sequences, right? I've given you the theorems that apply to sequences. You need to know what theorems work with sequences. And now I'm going to be giving you theorems for series, and you need to be able to distinguish between the two. That's part of the challenge, is knowing what you're talking about. But look, we're just getting into this. So let's give ourselves some time to absorb some of this. All right. All right, we've got to change gears just a little bit here. I think you have a big picture idea of what we're trying to do. We're trying to add up the pieces of a sequence. As of right now, we really only have one test that we can run that's relatively easy. If we take the limit and we get something other than 0, it's divergence and we're happy. But if that test fails, then we don't know yet, okay? So before we get to all these tests that we're going to learn, there are 3 important series. That we're going to learn first. Okay, the first one are what are called geometric series. So these series are a special type of series. They look a certain way, they behave a certain way. All right. The next one is harmonic series. And the last one is called telescopic, or sometimes they're referred to as collapsing series. All right. And we got to go through these one at a time. All right. So let's talk about geometric series first. Now I have good news. When you have a geometric series, you will always be able to tell if it converges or diverges. You'll always be able to figure it out. And it'll be relatively easy to figure that out, all right? But we first have to talk about what they are, okay? What do they look like? So a geometric series looks like this. All geometric series look like this. It is a number, A, plus A times R, plus A times R squared, plus A times R cubed, plus A times R to the 4th, plus ... forever. So it's like you have a number, right? A, that's always there in all of them. And then next to it, you have some number being raised to the 1st power, to the 2nd power, to the 3rd power, to the 4th power, blah, 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 forever. I will give you an example of this next to it. That way you can see it, okay? So here's an example of a geometric series. 3 plus 3 halves plus 3 fourths plus 3 eighths plus 3 sixteenths plus 3 32nds plus ... Now, why is that a geometric series? What do they all have in common?
Multiplication by half.
3.
Okay, yeah, and they all have a 3. So I could rewrite this one as 3 plus the next one I could write as 3 times a half, couldn't I? 3 times a half. And the next one would be 3 times a 4th plus 3 times an 8th plus 3 times 1/16. I'll stop there. And then someone mentioned that all of these 1/2, 1/4, 1/8, 1/16, they're all powers of 1/2, aren't they? Like I can rewrite this as 1/2 to the first power. 1/4 is 1/2 squared. This last one is 1/2 cubed. This last one is 1/2 to the 4th. Do y'all see this?
Mhm.
Yeah.
I don't see the 3, Professor. I see the 1/2 squared.
Well, they all have 3's in the numerator, don't they?
Mhm.
So you can just pull the 3 out in front of all of them,
Okay,
right?
I see them now. Okay.
So if we look at it this way, what would A be here? Look at the formula here. What would A be for us?
3,
3. And what would R be?
1/2.
1/2 raised to the.
Well,
Oh, yeah.
R is the thing
Yeah.
that's being
That's
raised, right? R is the thing that's being raised. So for all of these, R is always the 1/2. Do y'all see that? Geometric series? Okay, all geometric series, we'll be able to tell if this converges or diverges. All right, there's a way we can do it, but I need to show you how. Okay. So I need to finish writing up what I was doing on the left-hand side. Please agree with me that another way I could write this would be this. So I can condense this notation down to this notation. Every one of these has an A, so I can just slap an A here. And then I notice that the powers on these R's keep going up by 1, right? And my first one, even though there's not an R there, I could look at it as R to the 0. So it's like we have AR to the 0 plus AR to the 1 plus AR squared plus AR cubed. So it's like we want to start our exponents on R. We want to start counting at 0, and we're just going to count by 1 each time. And that's why I put n minus 1 up here. Does everyone understand that? We went through like an entire class trying to figure out patterns and how to write those patterns down, right?
Mhm.
Okay. So any questions about that notation? Okay, now the question still remains, what does this add up to be? Does it converge or diverge? So I'm going to show you, we're going to have a formula, okay? I'm going to give you a formula, but I'm going to show you where the formula comes from, all right? Show it to you because it's pretty awesome. It is pretty awesome. So here's what I want you to consider. I would like for us, yeah, let me write this down so that we all agree. So do you remember capital S was the sequence that we create when we add these up, right? Capital S. So S sub n should be A plus A times R plus A times R squared plus A times R cubed plus dot, 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 all the way until we actually stop here, A times R to the, you're gonna have to tell me.
R to the n.
So if I stop at N, where would I be?
1.
It's a little hard to see. Let me do it this way. Let's do S sub K. Maybe that'll make it easier. S sub K is the kth partial sum. So it means just add up the first K of these, right? So there's the first one, second one, third one, fourth one, fifth one. What would that last one be? That means if I
Infinity.
stop my sum at K, what
K
would
plus
be
1?
K, not plus 1,
-1.
minus 1.
Is it the same as R to the n -1?
Yeah, I'm using this formula right here. Look, if I'm asking you to add up the first 5, let's say, okay, let's write out what it would be. It would be, here's the first one, here's the second one, here's the third one, here's the fourth one, And then here's the fifth one. So look at what the power is. The power on the fifth one is actually one less than the 5, isn't it?
Mhm.
So that's why if I want to do S sub k, that's the sum of the first k. My last power on that last r will be the k take away 1. I hope that makes sense. All right, everyone, that's what the kth partial sum is. Do y'all agree with that? And I should mention, what I'm showing you right here, I would never expect any person to figure this out on their own, okay? I'm showing you where we're gonna get the formula from, and the way we do it is just, it's pretty freaking remarkable, okay? But let's just follow it and see if it makes sense. Does everyone agree with that line? That's true? Everyone believe that's a true statement? Okay? So now what I'd like for you to do is I'd like for you to take that answer that we just got, and I'd like for you to tell me what would happen if I multiply it by r. And you're like, what? Why in the world would you multiply that by r? So if I multiply the left side by r and the right side by r, when I multiply the right side by r, each one of these gets hit with an r, doesn't it?
Mhm.
Which means the powers on the r's go up by 1 each time, right? So the first one becomes a times r. What does the second one become?
AR
AR
squared.
squared,
Squared. Next one, ar.
AR cubed,
Next one, ar to the
the fourth,
fourth, and then dot, dot, dot. When we get to the last one, what would the last one be? AR to the
K.
just k, right? Just k. I understand you're sitting there, what are we doing, right? What in the world are we doing? So now I'd like for you to do this. This is even going to be crazier. I'd like for you to take this top row. I'd like for you to subtract the bottom row. So I'd like for you to take this and subtract this, and then subtract these rows. In other words, this is what I want you to do. I want you to do S sub k, take away r times S sub k. And let's see what would happen. So do you see that when you subtract, certain things are going to cancel? Like that AR, when we take this AR away, they cancel.
Mhm.
And then this one and this one cancel. This one and this one cancel. Okay, now is this one going to cancel? Is the one in yellow going to cancel?
No, I don't think so.
Is it? What's the one right before this one?
The
AR
last
to
one
what
up there?
power? What's the power on that R on the one that's right before it?
K minus 1.
K minus 1, right? So when I subtract, those are going to cancel. These canceled, those canceled, everything in the middle cancels, right? The only thing left is that A in the beginning, and then this A times R to the K at the end. Do y'all follow that?
So why are we getting to the point? I thought that when we're taking the sum, we're going to be at a higher number, but we're just stopping at K minus 1. Why is that?
Yeah. Well, we're only stopping at -1 here because that's what the formula of a geometric series is. The formula that matches this stops at n-1. I'm not sure if I'm addressing your question.
So, but where is it starting from then?
Starts at 1.
And stops at n minus 1 then?
No, 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 no. It doesn't. No. This right here, right there, that right there represents the infinite series, right? That's the infinite. It goes forever, doesn't it? Right? This goes forever.
Mhm.
What I'm asking you to look at is not forever. I'm asking you to look for just the sum of the first K.
Oh, okay.
So for right now, just look at the sum of the first K. The sum of the first K is this. Now, if I multiply that by R, I get this. And if I subtract, I take this and subtract this, I get the A from the front. And then I have to subtract this one. So minus A times R to the K.
So basically, it'll be the
You
first
apply
one on one series and the last one on the other.
That's right. The
That's-
first one on the first one, and the second one on the second one, or the last one on the second one are still there, but there is a minus sign between those. Do you see that? It is a minus sign?
Uh-huh.
Okay. Now, wow, okay, so what are we gonna do? We're gonna factor out on the left side an S sub k. And if I do that, I'm left with 1 minus r. And on the right side, I'm gonna factor out an a, and I'm left with 1 minus r to the k. And then I'm gonna divide both sides by 1 minus r. Do you all follow that algebraically? Algebraically, I just factored S sub k out. Here I factored an a out. I divided both sides by 1 minus r.
Yes.
Now, here's the beauty of what we just did. The beauty of what we just did is that we just found a formula for S sub k, didn't we?
Mm-hmm.
Now, what is S sub k? We already said S sub k is a plus ar plus ar squared plus ar cubed plus dot 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 ar to the k minus 1. That was this line right here. That's what S sub k is, right?
Mm-hmm.
But we just found a nice, better formula for it right here. And so if we want to know what this sequence does, we need to just take the limit as in this case, k goes to infinity of this thing. So where's this thing going? If I let k go to infinity on this
Still
formula right here.
Infinity.
I didn't hear that, I'm sorry.
Is it infinity over a number?
What's going to infinity? What's
Okay.
going to infinity here?
K.
K, okay, so k is just this exponent, right? All right. Let's just take a breath, all right? All we have to figure out right now is what happens to this piece, r to the k. If I let k go to infinity, what's going to happen to that?
It gets bigger.
Sometimes. Does it ever get smaller?
Yes, if it's 1 over 10 or something like that.
Yeah, so this is what I started class with today. Remember this? I said, let's say we have something that looks like r to the n, and I let n go to infinity. Then this thing will go to 0 whenever r is less than 1, right? Between 0 and 1. But it will blow up and become divergent if r is bigger than 1. Right? Remember I said that? So here, what I can say is that if r is bigger than 1, right? What if r is bigger than 1?
It's going to be divergent.
It's going to diverge. This whole thing will go to infinity. Then S sub k goes to infinity, and that means it diverges. Now, if 0 is less than r is less than 1, now I know that when I let k go to infinity, this thing goes to 0, doesn't it?
Yes, and it's convergent. So this is basically a sequence.
That's right. It is a sequence.
Okay.
What does it go to, though? Hold on. What does S sub k go to? If that thing goes to 0, what does this go to?
It's convergent 0.
No.
1.
Infinity.
No. If this right here goes to 0, then what is left?
0?
No. If this thing is gone,
1 over 1 minus r.
a times
1 minus
1 minus
1.
nothing. So a times 1, which is
A.
over 1 minus
A
r.
1 minus r.
Which definitely means we have convergence. Okay. We have a conclusion, all right? We have a conclusion. And now I'm going to go and have you look at the formula sheet. your second formula on here has to do with geometric series. It says, if you have a series that looks like this, now it has to look like that for you to use this test. Then it will converge and it'll actually have a sum of a over 1 minus r. Isn't that what we just got? A over 1 minus r? That will happen as long as the absolute value of the r is less than 1. Now, if the absolute value of the r is bigger than or equal to 1, this series will diverge. Okay? Let's do a couple of examples. Let's do a couple of examples of geometric series.
Do we have that sheet anywhere in our files or something?
Yeah, it's there. It's in Canvas under files, under formulas you can bring to tests. All right, let's do an example. We want to figure out sum n equals 1 to infinity of 4 times 1/3 to the n minus 1. Okay, you have to recognize that that's a geometric series because it looks like this. That's what a geometric series looks like. So for us, what is A?
4.
4. What is R?
3rd.
1/3.
1/3, right? Okay, let's check. Is the absolute value of R less than 1? Is it? Yes, right? So since it is, we know that this converges. In fact, it converges to what?
To 0?
A over 1 minus R. Right, that's what it converges to. We just derived that formula. So that means for us, it would be 4 over 1 minus 1/3, which would mean 4 over 2/3, which would mean, is that right? 6? It converges to 6.
So I have a question.
Yep.
Would we have to state that we're using the geometric series test, or can we just go straight into absolute value of r is less than 1 and then put like a check mark next to it and just be done with that and just go straight to the answer?
Well, on a test, I would put what test you're, on an exam, I would put what test you're using, only because there's so many tests that you're going to have to choose from. It would help me understand what you're doing,
Okay.
rather than me trying to figure out what you're doing. You know what I'm saying?
Sure.
Yes.
Are there any tests, like for example, that may be applicable for, like for instance, if we're trying to find if a series is convergent or divergent, instead of just the n test, even if we use more than 2 tests, they can have the same answer? Are there tests like?
I think I understand your question. Are there some series that you can do different tests on them and you get the same answer either test?
Yes.
Either way, you get the same answer. So
Yes.
maybe one test is a little easier than the other?
Yes.
Yeah, Yep. Now, you're not guaranteed that you can do it with different tests, but yeah, it can be done multiple ways sometimes. Let's do another one. How about this one? Is that geometric?
Yes.
Yeah.
Yeah.
All right. A is 4. R is 3. Is the absolute value of R less than 1? No.
No.
What does that mean?
Divergence.
Version.
Does it seem okay?
How do we know it's not smaller than 1?
R is 3,
Okay, yes.
right?
So
How about this one? So does that look like this? I've been very nice so far, and I've made everything look exactly like that, haven't I?
mhm.
You can see what A is, you can see what R is. Everything's great. Does that look like a geometric series then? Sorry, I made some beef jerky. First time I ever made it. It's really good. Can't stop eating it now.
That's too crazy. I was actually about to do the same thing in the next couple of days.
Good stuff. Okay, so look, this does not quite look like this, does it? And the big thing that we have is that this has n-1 in the formula, right? This
Mhm.
doesn't. And you can't just sit there and go, oh yeah, well, n+1 is the same as n-1. Nope, you can't. So you ready? Here we go. Magic time. What did I just do?
Visible 0.
Mm-hmm. So look, that n+1 power, I want it to be n-1, don't I? So I wrote it as n-1 plus 1, but I already had a +1 there. So I introduced a hidden 0. We've played this game before, haven't we? Same with the bottom. I wanted it to be n-1. So I put n-1, but then I had to +1. Now at this point, this is just algebra. This can be rewritten, sum n equals 1 to infinity of 3 to the n-1 times 3 squared over 4 to the n-1 times 4. I'm using properties of exponents backwards. Essentially splitting that there and there. Do y'all understand that and agree with it? No questions? These two are both raised to the n-1 now, aren't they?
Mhm.
Okay, so I'm going to write it like this. Okay, now we still have a 3 squared and a 4 here now, don't we? Do you see that?
Yeah.
So I'm going to write that in front as a 9/4. And then since the 3 and the 4 are both raised to the n-1, I'm going to make it 3/4 to the n-1. Applying the power outside a fraction like this. Now, are we geometric? We are now. A is 9/4 and R is 3/4. And the absolute value of R then is less than 1. And so this will converge. What does it converge to? A over 1 minus R, right? Which for us is 9/4 over 1 minus 3/4, which is
9.
9.
Is it 9? Yeah, it's 9/4, and then that becomes 1/4, and then you flip it, it becomes 9. Okay. What do y'all think? Pretty exciting, huh?
So here, what you did, can you go back to the example?
Yeah.
So what did you do? Because I think 3/4 was less than 1. Shouldn't it be like converge?
It did converge to 9.
Oh, my bad.
Oh, no, okay,
I'm sorry.
that's fine. Because R was 3/4, and the absolute value of that is definitely less than 1. I'll never forget, I think I was in 5th grade, and my science teacher had this question for us. She said, what would happen, and she was doing this in the classroom. She said, okay, here's the walls of the classroom. She was standing over here, and she said, okay, class, if I start at this wall and I walk halfway across the room and stop, and then walk halfway again, okay, half of that, so to here, and stop. So she stops here, and then she walks halfway again, stops, and then halfway again, stops, halfway again, stops, halfway again. Her question was, will I ever reach the other side of the wall? I remember that. It was like 5th grade, and I was sitting there going, I don't know, I'm not sure. Will you?
No.
Let's think about this, okay? Believe it or not, this is a geometric series. Okay, so look, how far does she walk in the first distance? Let's just say that the distance from here to here is 1, okay? So when she walks the first halfway, she walks a half, right? Half of that?
Mhm.
So we have a half. Plus, now, how far does she walk in the second part? From here to here? Well, that's half of halfway, isn't it?
Yes.
Half of halfway is 1/4, isn't it?
Mm-hmm.
And then she walks half of
1/8.
half, which is 1/8, plus half of a half of a half, 1/16, right? And
Mhm.
she's going to do that forever and never stop. This is a geometric series because this is 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the 4th plus dot, 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 right?
Mhm.
You buy that? Now we need to write that as a sum. So can we rewrite this as a sum right now? All right, just think about what this is. This is 1/2 to the first power, 1/2 squared, 1/2 cubed. So how would I write that?
1/2 n minus 1.
Just n. Just n, because we need to start at 1, don't we? We need to start at 1. So this is the way I have to write it. Now, Cameron, in order to make it geometric, I need to make that n be an n minus 1. So do y'all see, I took the problem here, I converted into what we're actually doing, 1/2 plus a 4th plus an 8th. I noticed that these are all powers of a half. I rewrote this in sigma notation, and now I need to make it look geometric. So to make it look geometric, I see the hidden 0 again, good. I'm gonna go 1/2 to the n minus 1 plus 1. I've got to force that -1 in there. Get used to that, okay? Everyone get real used to that idea because it's going to be there. From
And not
here
you just use just a 1 there,
I'm sorry?
just +1. Oh, then it would be 2. It'll start at 1/4 then.
Yeah, if you just, wait, if you did what?
If I just add n plus 1, so it'll just start at 1/4.
That's right, you'd be
And would
missing.
skip 1/2.
Mhm. So everyone's okay from here to here?
Yes,
Like
sir.
this algebra from here to here is important. That you understand that. And look, if you look at it this way, this is A and this is R to the n minus 1. Do y'all see it?
A to the 1. I mean, it's clear that the 1/2 is to the exponent is 1, correct?
Yes, yes, this exponent here is 1. Mhm. So does that converge?
Yes.
It does, right? It converges because R is 1/2. That's smaller than 1. What does this converge to? A over
It's 1.
1 minus R, which is 1/2 over 1/2, which is 1. Does that make sense that it should converge to 1?
Yes. Because your teacher.
We're getting closer and closer to 1, right? Are we ever getting there?
No, yeah, because it wouldn't get infinitesimally small.
Yeah, we're going to be real close. See, the idea is this. If we could add this forever, if we could, that would be 1. But I mean, we can't ever add it forever, so it's converging to 1. We're getting closer and closer. The further you go out in the sum, the closer and closer you get to 1. Right? That's what it's saying.
Mhm.
Now, I can illustrate this back here on this thing that we started class with. Let's take the example I just did. So that was 1/2. Oops, 1/2 raised to the n. Yeah. There we go. I've kind of already blown the idea. So if we just look at the first one, it's 0.5. And as I start going out, look what's happening. 0.99999, boom, I'm at 1. Look at that already. The computer's already rounding this to 1, okay? I got to back up, let me see. So if we go out, look, we only have to go out 20, I'm out 20 places. So I've added up the first 20 of these. I've added them up and I'm already at 0.999998. I'm really close to 1 and I've only added the first 20. If I keep going out, I will never exceed 1. I'll never get past 1 ever. Let me see here. Yeah, okay, that's all I want to say about that. So I think her question is still unanswered. Like theoretically, I don't know, do you ever get there? You can't keep walking forever. You can't keep going half. You can't cut half and half. Physically, you run out. So it's an open question, but in mathematics, that series converges to 1. We're getting closer and closer. All right, last example, because we're almost out of time. Have y'all ever seen this before? If you take the number 1/3, we all know that that's 0.3333 forever, right?
Mhm.
Okay, so couldn't I rewrite that as 3/10 plus 3/100 plus 3/1000 plus 3/10,000? I mean, that's what each of those decimal places means, right? This is 3/10. Then we add to that the next one, 3/100, then 3,000. Yes or no? Yeah? Okay, do you all see that this is just 3 times 1/10 plus 3 times 1/10 squared plus 3 times 1/10 cubed plus 3 times 1/10 to the 4th, right? Isn't that what this is?
Going towards 0.
They are going to 0, but I'm trying to get you to see we've got geometric here.
Mm-hmm.
Let's rewrite this in sigma notation. I know I've got a 3 for all of those, right? There's a 3 there for all of them. And then I'm going to start at 1/10. What's the power I start at here?
1.
And
1. So I'm just going to go n. Now, that's not going to work for geometric, right? I'm going to need that to be in -1. So I'm going to just go ahead and do that right now. -1 plus 1. So what we get is this, sum n equals 1 to infinity, 3 times 1/10 to the n minus 1 times 1/10 to the 1. The 3 and the 1/10 can come together. Your hand hurt yet? 3/10 times 1/10 to the n minus 1. What hurts worse, your hand or your brain?
Both.
Both. All right,
Not
do you
yet.
see how I've converted this to a geometric series?
Yes.
Okay, let's see what this turns into. A here is 3/10 and R here is 1/10. That should converge. It should converge to A over 1 minus 1/10, which means we have 3/10 over 9/10.
That's funny.
And if you do that, you get 3/9,
1/3.
which is 1/3. Which is exactly where it all came from, isn't it?
Right.
Yeah. Now I'm showing you that because now I have another question. What would, if this repeating decimal that I just showed you, if that repeating decimal can be rewritten as that fraction, then what could you say about this repeating decimal? Not 0.333 repeating, but 0.0333 repeating.
That would be to 1 to the third to the n.
Don't know. We have to figure it out. Let's see what does this decimal represent. Notice we have a 0 here now, right?
Mhm.
So we don't have that 3/10 anymore, but we do have the rest of it, don't we? Don't we have the rest of this?
Yeah.
Okay, so we have 3 over 100 plus 3 over 1,000 plus 3 over 10,000 plus 3 over 100,000. I can rewrite that as 3. Can I write that as 1/10? 1/10 to the what power? Second, right? 3, 1/10 to the third, 3 times 1/10 to the fourth, dot, dot, dot. Take that to sigma notation. 3, okay, what am I gonna have here? 1 over 10 to the
N plus 1.
n plus 1, good. N plus 1, see, because we need to start at 2, don't we? 2, then 3, then 4. 2, then 3, then 4, not 1, 2, 3, 4. So we start at n plus 1. But what do we need for it to be geometric?
Minus 1.
N minus 1. So we're going to have to go in there and get a hidden 0. 1/10 to the n minus 1, and then 1/10 to what power?
Squared.
Squared. It will be 2. What's 1/10 squared? Let's go ahead and put that with the 3. We should get 3 over 100. I'm almost out of time. That's why I'm working so fast through this. 3 over 100 is the first part, and then we have 1/10 to the n minus 1. And now we finally have it as geometric. So this should converge. There's your A, there's your R. So it should be 3 over 100 over 1 minus 1/10, which gives you 3 over 100 over 9/10. And this, I believe, turns into, hold on, 3, the hell is that?
30 over 900.
Minus
100 times 10 over 9.
1/30th?
This comes the 9, we flip it, right? So it should just be 1, 3,
It's fun.
1, 10. Is it 1/30th? Is that right?
Yeah, that's what I got.
Yeah, check it on your calculator, 0.033333.
So how are you getting 1 minus 1 over 10?
This right here,
Yes, sir.
I'm using the formula A over 1 minus R,
Oh, okay.
right? I identify what R is, I identify what A is. We're at a time. Here's something that would be, well, no, I won't even give you that. That'll be a little bit tough. So in your homework for this section, we're just, I mean, we just started the section. Like we're just barely through. We still have to talk about harmonic series, telescopic series. For your homework, I think you should definitely look at problems 7 through 12. Because numbers 7 through 12 are all geometric series. And they tell you that, okay? They ask you to determine whether or not it converges or diverges. And then it says if it's convergent, find the sum. All right, what is it, Tuesday?
Tuesday.
Okay. I owe you a test, right?
No.
I agree.
No test? You know.
We should all get A's.
It's a freebie 100.
So here's what I'm gonna do on this test. Where is it? There it is. I'm gonna send it to y'all in just a minute, but here it is. So initially I had told you that I wanted this to be due on Friday at 9 a.m.
Mhm.
I'm just gonna make it due a week from today. All right. But there's a couple of things, right? You got to keep up with your homework. All right. The 8.2, the 8.1, got to keep up with it. The other thing is, if you want to know your grade so that you can determine whether or not you want to drop the class, drop date's Friday. Okay. So the only way I can give you feedback is if you turn that exam in on Friday. All right. But I want to give people time to do the test and have a little bit less stress with it. But if the drop date is something important to you, you're just going to have it to me by Friday at 9 a.m. All right. Otherwise, if you're not so concerned about the drop date, I don't mind getting it Tuesday. Okay. Now you need to read these instructions. Evaluate the integral, show all your work. I want you to go and take this integral all the way. Okay. Find the area, right? Label the graph, write your answer as a decimal. There are certain ones where I tell you do not do the integral. Set up the integral, don't evaluate. I told you that maybe I was going to just have you do the integrals on the computer. No, if I say don't evaluate them, don't evaluate them. Just leave them in the form, you know, just where you have the formula set up. Okay.
So I have a question real quick.
Yeah.
So I can't do the test today or tomorrow, but can I still come in for like tutoring before I take the test and have you just throw problems at me?
You can ask me questions anytime between now and Tuesday. I mean, I'll limit what I tell you, but if you need a push in the right direction, I'd rather you talk to me than go try and find answers somewhere on the internet, which I think will be very difficult to do with this test. Yeah, because these problems are a little, these things right here, these are, enjoy, right?
Also, we're also covering chapter 8 on this.
8.1, just 8.1.
Oof. Okay.
Just 8.1. So I give you some things, you have to find a formula, do these converge or diverge, and then show that this is a monotonic and bounded. 8 questions.
Is this going to be like the last test where you just do 6 of them and the other 2 are extra?
I don't think so. No. No.
Okay. And then my last question on number 1, let's say we like figure the integral out and we just gotta like find the limits. Can I just go on my calculator and just type in like the integral that we found with the limits? Because it'll just tell me, like it'll just calculate it for me without the work. Can I do that? Is that possible? I mean, I could write it out, with like the
Yeah, I would say side on showing me more of your work and relying less on the computer. Only because this is a take-home test, right? So because it's a take-home test, if I want you to evaluate the integral, that means that I want you to take it the whole way. Like I want you to do that means you have to find the antiderivative of this. You can't go into Wolfram alpha and find the antiderivative. You need to show me all the work, right? So if you've done all that already, you may as well just plug the numbers in.
Okay.
You know,
Can do.
yeah. And also I will say, feel free to use a computer to help you graph things. Like if you're having trouble figuring out what these graphs look like, please use a computer to help you. All right. I am expecting you will do that because some of these are going to be, you know, maybe a little bit weird to look at. Like you may not know what these look like. So use a computer, graph it. But when I tell you to set up the integral, I want you to give me, you know, include the drawings for each part. The drawing should support your integral formulas. That means take your time to just show me pictures, you know, draw me the function. I'm giving you extra time because I want you to take your time through this. I don't want you to rush through it. I don't want you to try and force it.
Can you go back to one?
Yeah, I'm gonna send it to you right now.
So is it just like we don't have to find the formula like a volume or surface area for the, we just need to evaluate it, right? Correct?
Which one are you talking about?
For one,
Yeah, evaluate the integral.
just simple integration. Okay.
I don't know about that.
Is number 3 supposed to be ln x squared minus x plus 2, or is that correct, x minus x?
ln x minus x plus 2.
Okay.
No. You need to remember why this integral is on here. There's a reason why this integral is on here. Well, you'll see.
I don't even remember
Yeah,
what this is. So I go back.
Yeah. So look, between now and Tuesday, if you have questions, just contact me, okay? Just contact me. Come to my office hours or something. All right,
Definitely
everyone.
will.
I'm going to email this right now. Make sure you keep up with your homework. As you can tell, 8.2 means no joke. Like we're going to start getting pretty into it here. So keep up with it.
Okay.
All right, I'm going to send this out right now to the class. Oh, come on.
All right, sir. Have a nice
Have a good one. You too. And 3 due Tuesday. I'm gonna make it due at noon. Or 12:30. We can go to class at 1, right? So 12:30.
Sure.
Are you setting it up on Canvas?
I'm gonna send it through Canvas right now.
Okay. Okay.
Thank you very much.
All right.
See you on Thursday.
Yep. See you.
See you. Have a good day, sir.
Bye bye.
Have a nice day.
Okay, just went. Well, it's thinking. There it goes.
I feel bad for your computer sometimes
Why?
because I feel like you're taxing the hell out of it.
Like resources?
Yeah.
I don't know. I did pretty good. My CPU, I'm running a lot of things right now. I've got Mathematica running in the background. So my RAM, I'm not too bad. What's using the most memory here? Firefox is using the most damn memory.
Yeah.
Yeah. My CPU's trucking along. Yeah, I'm okay. I think I've got an i7 on this one because I'm using a desktop. Yeah, I've got an i7 and
700. Yeah.
I got 60 gigs of RAM, so I should, I do okay with 16. We're not there yet where I need more than that. I don't do any gaming or anything, so.
But then it's weird the way your computer keeps crashing.
That's something else. You know, I think that has something to do with my not touch screen, my interface here that I use with my stylus. There's something that when I touch it and I've got something else going, because I've got multiple inputs. So I can use this thing, which allows me to just draw right on any screen.
Mhm.
But then the thing I'm drawing on has its own.
Oh, so it doesn't, okay, it doesn't know what argument to take. Okay.
It's like it gets confused for just an instant, and then it's just like, "Boop, I'm out of here, blue screen of death." Yeah, I haven't figured it out yet. All right, I gotta go. 2:50.
Oh, yeah.
Okay. Y'all
Thanks,
good?
Professor.
Okay.
See you
y'all
later.
good?
Bye.